check your email. I sent you something last week. Yeah, I think I sent some email about maybe some copies that you missed the check-in window. Yeah, actually I wanted to find some time to check the copy and give you something by email, but I couldn't. Inshallah, I will try. Hopefully, maybe by the during the break if I have some time, or just immediately after the break. I hope, inshallah. Yeah, that's actually there were two people who made that request, who missed that window. I'll try my best, inshallah. I mean, I try to find some time to do that, but it's not easy. I mean, yeah, because I'm kind of very busy. But yeah, I will try, inshallah. Yeah, somebody else, you're welcome. All right. So let's, no more questions. So I start talking about this mathematical induction. Now, this mathematical induction is actually a very easy way how to make some type of things that uses some sort of recursion. It's similar to the fact that you're using something at a state, and then you're going to assume that state is true, and then if it is true, then you're going to prove that the next step is going to be true as well. So let's try to understand these by maybe just have a look at before these, and then we come back into that to understand the actual induction, what it is. Now, the idea behind this induction is that if we imagine we have this kind of ladder, where this ladder has an infinite amount of, let's say, steps, or what they call them, rungs. So the idea behind this induction is that if I can prove that the first step I can reach it, and then all I need to do is to prove that if I'm in one step, I can reach the step that is after that. So I'm assuming that there are two things that I need to do. The first thing is that I'm trying just to find this. I need to find that I can actually reach this first one, and then if I'm in one, I can go to the next one. So these are the two things that are part of this mathematical induction. There are two steps, two parts that I need to prove. The first one is that there is a first step that I can reach, and then the second thing that I'm going to do is to prove that if I'm in a step, I can reach the next step. And that's the basic of this mathematical induction. Now let me just go back and see. Okay, so this is, so that's it. So the proof by mathematical induction has two parts. The basis step, this is where the step that I'm going to test and check that actually this proposition that I have is going to be true for the first element. So this P of n, whatever the P of n is, I'm going to prove that P of the first element, P of 1 or P of 5 or P of 700, whatever the first element that will make that P of 1 of the first element to be true, I'm going to make sure that X is true, and then once I have that, I'm going to use this inductive step, and the inductive step is that it shows that if P of some k is true, then P of k plus 1 is also true. So this is what I need to prove. So let me just get back into like maybe a slightly different way how to present things. So I'd like to prove that if I have such P of n, I need to prove two things. The first one is that for the first element, I'm assuming 1 is the first element of the n's, the positive n's. For example, if n this is positive n's, that means 1 is the first one. And then so this one is true. I'm going to show that this one is true, and then I'm going to assume that if p of any k is true, then this is supposed to be this conditional. If p of k is true, then p of k plus 1 is also going to be true. So that's the main thing. So now let's test it with this example, proposition 1. Now the sum of the first n positive integers is n times n plus 1. So this is the proposition that I'm trying to prove. Now, just to have an idea, what are we talking about? I mean, remember if we did the summation. Now, if you remember, we said the summation, and then with some k is equal to 1 until some kind of whatever n, or actually the sum of k, whatever it is, this is going to be equal to this number over here. So that's, we've seen this. This is the closed form of this summation. If you remember, we've seen that. If you don't remember, that's fine. But let's just see that actually we can prove that that's the rule that and it works. So let's see. For example, the sum of the first n integers, assuming that n is going to be 1. Now that means I'm going to have only 1. So n is equal to 1. That gives me, if I place 1 here, that means 1 multiplied by 1 plus 1, which makes it 2. So that means 2 divided by 2. This gives me 1. And the sum of the first n numbers, with n being 1, that means the sum of 1 is going to be 1. So this is what it gives us. Using this second one here, this one over here, is taken from applying the formula here with n equal to 1. So we just show that this is the sum when n is equal to 1, and this is the result of applying the formula that we have. Okay, let's try just to make sure that we understand. If n is equal to 2, that means we need to, the sum of the first n numbers is going to be 1 plus 2, which gives me 3. Now if I apply this, replacing n by 2, it's just going to be 2 times 2 plus 1, which is 2 times 3. And then just simplify by the 2's. What is remaining is the 3, which gives me 3. So basically it just shows you that this is the rule that we can have. And now this is just a rule. I'd like to prove it by mathematical induction. Now all I have to do is to prove that it's true for p of 1, and then if it's true for some p of k, then p of k plus 1 is going to be true. So let's do that. Okay, maybe let's do it, and then we let, I think the example is solved a little bit later. Let me just do that on here. Then we can see the solution here. So the idea is, again, we would like to show that if this is true for p of k, then it's going to be true for p of k plus 1. So, okay, so what is the induction hypothesis? The induction hypothesis is the thing that I'm going to assume. So what am I assuming? So I'm assuming that if p of k, then p of k plus 1 is going to be true, which means here what I need to show, actually hold on, let me just, I need to show that, where is this? If p of k, then p of k plus 1. What is p of k? In my case, this is k times k plus 1 divided by 2, which what I did is just take this, replace n with k. So as what I'm trying to prove is that if this is true, that means p of k plus 1 is going to be this. If this is true, then k plus 1 multiplied by k plus 1 divided by 2 is also going to be the sum of the numbers from 1 to k plus 1. So notice that what I did here is just I replaced this k with k plus 1. That means this one here is k plus 1, and this one here is this k plus 1, and then we have this plus 1. That's why I kept it separate. So now this is not the way I'm going to show it. I'm just going to make it easy. Now if I say that this is true, that means what I need to show is that I need to show that k plus 1 divided by 2, if I add to it k plus 1, then it's going to be equal to this k plus 1 times k plus 1 that I just said divided by 2. So this is basically what I'm trying to say. P of k gives me this. P of k plus 1 is going to give me this. So that means if P of k, I'm just going to add, because we said that P of k is the sum of the k integer numbers from 1 to that k. Now if I would like to have P of k plus 1, this is going to be actually, let's write it this way maybe. This is going to be P of k, P of k plus this k plus 1, this first number, this next number that I'm trying to add. All right, what is it? And what I'm trying to prove, what I'm trying to show is that this is going to be equal to this. But let's take it one step at a time. So this is what I need to show. This is my assumption. This is what I need to show. So how to go from there? Okay, let me go down. All right, I need to lower the sound a little bit. Okay, let me just show a little bit up. Yeah, I would like to show this. So I'm going to start from here. So this part over here. This part over here, what I need to do is that I'm going to try to write it differently by trying to put everything divided by 2. So plus here. So how to make this, all of them to be divided by 2, and I can see later on if it's going to reach that. So this is going to be equal to what? Well, all I have to do is to multiply by 2 and divide by 2. It's going to be the same thing. I hope everybody is still with me, right? So far, nothing too crazy. Just what I did is that I multiplied by 2, divide by 2. This is going to give me this k plus 1. But now that I have them into this, I'll try to represent them in a way that is going to be like this. So let's now try to simplify this. I mean, like not simplify, but try to expand. So this is going to be k squared plus k, this part over here, k squared plus k, right? Plus, what is it? 2k plus 2. This whole thing divided by 2. So all I did is that I expanded these. This is 2k, this is plus 2, and this is k squared plus k. Nothing fancy. Let's just keep going and see what we get from there. So this is going to be k squared plus 3k plus 2 divided by 2. Now, just to make it simple, to minimize my guessing, let's try to expand this. This is what I'm trying to reach. I would like to prove that this thing is equal to this. So let me try to simplify this here over here. So this is basically, this is equal to k plus 1 multiplied by k plus 1 plus 1, which is k plus 2. So this whole thing divided by 2. Now let me expand again that part just to see if I'm going to get something similar or equal to what I have there. So all divided by 2, but then I'm just going to have, this is k square plus 2k, and then 1k plus 1 times k plus 2, which is going to be k square plus 2k, sorry, plus 3k, because 2k plus 1k, that's 3k, plus 2, the whole thing divided by 2, which turned out to be, okay, exactly the same thing as what I was trying to reach. So here, all I have to do is to factorize by k plus 1, and then I'll have it multiplied by k plus 2. So what I did, let me just backtrack a little bit. The first thing we did is that we proved, okay, the first thing I said doesn't show up here, I forgot. So we proved that p of 1 is going to be, is true, that it's possible to do it with the first element. And then we try to prove that if I assume that p of k is true, which is, this is what I did here, then p of k plus 1 is going to be true, should be true. So I just use p of k, which gives me this, and I'm going to add p of k plus 1, that means it's going to be the sum of that plus k plus 1. And based on that, what I did is that I just expanded, try to put that on the same divisor of 2, and then the rest is just, it's amazing, expanding and then simplifying, and this basically is going to end up being the similar to what I'm trying to prove, which is going to be equal to this k plus 1 multiplied by k plus 2, which is k plus 1 divided by 2, which is this p of k plus 1. So this proof by induction, this is what I did. It just started by showing that it works for one number, and then based on the assumption that it's true for p of k, then I need to prove that if this is true, that means p of k plus 1 is also going to be true. And that's the mathematical induction. So let me just try to find out. I mean, I think I've seen it some. Oh, is it not here? Okay, that's the one. Yeah. So that's this example one that shows the proof of that. So if we'd like to show that if n is a positive integers, then this 1 plus 2 plus etc. plus n is going to be equal to this. So this sum, that means p of n is going to be that the sum is going to be equal to that. So we must do two things. We must prove that Pn is true for one number. We'll show this is what you need to show, that for the first one, at least for the first one, it should work. If it works for more, that's great, but we need to show only for the first element this is going to be true. And then we assume that we need to prove that if we're going to assume that this is true, if this is true, then we're going to show that p of k plus 1 is going to also be true. And that's the inductive step. So the basis step is that we prove that p of 1 is going to be true. So the first one. And then the inductive step shows this hypothesis that we assume that p of k is going to be true for some k. And then what we need to show that if this is true, this p of k is true. Now if we add k of 1 to it, it's going to give me, this is the result of p of k plus 1. And that's what's shown here. That's why I wanted just to show it here in a more different step. Probably this one is much neater. So that's why the summation on the left side is p of k plus 1 is k plus 1 more than the summation for the left side, p of k, yeah. So anyways, I hope that clarifies the thing. So the basis step is when we check that the first element, it works for that proposition of ours, and the inductive step shows that we're going to make an assumption that this is true, and if p of k is true, then we need to prove that p of k plus 1 is also true. So we assume that this is true. This is what we call this inductive hypothesis. We assume that this is true, and by assuming that this is true, it has some properties. That means it's going to be something like this, or this this here is going to be p of k plus 1 is going to be like that. So once we assume that, then all we need to prove is that p of k plus 1 is going to follow the same pattern that we use here, which is going to be p of k plus 1 is going to be this k plus 1 times k plus 1 divided by 2, which is the thing over here, which is this k plus 1. So that's the main idea. And then if we're able to do that, then it works out. So let's find some other example, maybe to make sure that we do it properly as well. Let's say the other example here. Let's have this proposition number 2 that says if p is any prime number, then 2p minus 1 is also a prime number. All right. Now let's just try for some special cases. Okay, so p. So for example, if p is a prime number, we did not start by 1 from 1. Why? Because we said that, remember, we said that prime numbers starts from 2 onwards. Because a prime number is a number that can be divided by 1 and itself only. So that means we're not going to be using 1. 1 is not a prime. So the first prime that can be p is going to be 2. So let's try now 2. If we say the prime is 2, so 2 power 2 minus 1, is it going to be prime? Well, let's find out. So this is going to be 4 minus 1, that's 3, which is prime. Now we can keep trying for some others just to be confident that actually the rule is true, but the idea is that we need to prove that it works with 1, and then now let's assume that it is true for some k, and we need to prove that it's going to be true for some k plus 1. Okay, so let me try to find out. Okay, no, it's not here. I thought it was here. Okay. So let us do it. So if we say I wanted to find maybe a way. So let's find out. Okay, so what did they say? Since 3 are all primes, we maybe said for this is always true, but if we try the next prime, 11, we find that 11 minus 1 is actually not going to be prime. Oh, interesting. Oh yeah. So it is not prime. So our general assertion is therefore false. So it is true. Imagine getting a computer. Okay, so actually this is kind of this rule. It works for the first few numbers, but then it doesn't work for when numbers are going to be becoming 11. Okay, so let's see. Okay, let's try to find out if we can prove. Now, if we cannot prove it, then it will show up that actually maybe p of k, this p of k is not going to be deducting p of k plus 1 is going to make it true. So if that means we're going to lead to some contradiction of some kind, and then it will just cancel that this is not going to be a rule that I can prove. So let's try. So if we say p of k is going to be like 2 power k minus 1. And if we say that it is a prime, So that means if k is a prime, this is going to also be a prime. So this is also a prime. Now, if that is a prime, p of k plus 1 does not mean, actually this is the thing, k plus 1, see, I did not add by 1, this is here, I add by 2, it's 5 plus 2, that's going to be 7, this is 2, this is k plus 1, so actually, that's why actually it doesn't seem to be some kind of, this is like some kind of linear progression that I can just keep adding here. So for example, this 3, that means the previous k plus 1, fine. But this one here is not k plus 1. So it does not work. Actually, just from the first ones, I can spot that there's something not linear about it. Okay. So that's kind of... okay, I'm trying to read what's the justification they came up with. But if we try the next prime, 11, we find out, all right? So it is not prime. Assertion is therefore false. So what we assume is that if we have some p, so let's say for k is 7, then k plus 1, even that k plus 1 is going to be 11. So that's not k plus 1 anyways, that's k plus 4. So anyways, I think just the fact that we cannot have this k plus 1, that's the thing. This doesn't apply to this. This mathematical induction doesn't apply to this one, and actually therefore, actually even this whole thing, this whole rule is not true. But if I'm trying just to see from here, for example, if k was my 2, k plus 1 is 3, that's fine. But if k is 3, k plus 1 is not 5, this is k plus 2. So actually there's no consistency. This is also k plus 2, but the next one is k plus 4. So it's, yeah. I think what the point here is by making is that even though I need to just check the first one to make sure it works, I need to prove that for the first one it works. It's worth trying to see try to few next ones, like what was done in the here. Try to few next ones just to make sure that actually, just to be confident that there's something going on. There's some likelihood of this working. And if we just do it this way, see, it looks like the progression is not that clear. And then it shows up basically that with this 11, it gives us this 2047. We just trust them. If you'd like to calculate that, it's 2 power 11 minus 1, which is most likely going to give us this. And this is not a prime because prime is just divided by itself and 1. So it's not a prime. As long as there's some kind of other multiplications that can be gone through, so it's not a prime. So that's the idea here, is that we need to check a couple of times just to make sure that actually this works. So that was not a good way to go. Let's try it with this one. Maybe. Okay, that's just explaining the mathematical induction. Basically, what it says is that you just have the things that are stacked next to each other, and then if you just bump one of them somewhere, even here, if you bump one of them, what it happens is that from that it's just going to, all of them are going to start falling. This is the idea. So let p of n proposition that domino n is knocked over, so any n somewhere. If the first domino is knocked over, that is p of 1, that's the first one is knocked over, and that is then if the kth domino is knocked over, it also knocks the k plus 1 domino, and that's the idea behind the induction, that if this one is true, then the other one is going to be true, etc. So this domino effect of like induction. I think that's what this example is about. So let's the principle of let's have a look at this. Okay. To prove that p of n is true for all positive integers n, then p of n is a propositional function. We complete 2 steps. We verify that p of 1 is true. Even though we say 1 doesn't have to be 1, sometimes it's the first element, the initial step, by what we start. The first number that is going to be, maybe in some cases, the first number is going to be 3 or 2 or 5 or 2000 or whatever it is. forever the rule that we try to apply. But they say, if we say here this is for starting for the numbers starting from 1 onwards, that means we're going to start from p of 1. So we verify that p of 1 is true, and then the inductive step is that we show that if p of k, then p of k plus 1. All right, so let me try another example. So we've seen this one. Okay, so these are some guidelines. A template for proofs by mathematical induction. Express the statement that is to be proven in the form of for all n bigger than p. Okay, maybe let's try more examples, then we go back to this. Okay, now using this mathematical induction to show that the sum of the first n positive odd integers is n square. Okay, let's play with that. Control all, so delete. So what we're trying to do is, okay, we don't need that. We'd like to prove that the sum of the first, let me just check this. Okay, I'm trying to not use the mouse. Okay, that was not how it was meant. All right, let me paste this. Okay, so that's what I would like to prove. The first n positive odd integers is n square. So what are the first positive odd integers? So we have 1, we have 3, 5, 7, 9, etc. So basically what we're trying to do is that if n is going to be equal to 1, the sum of the first one positive odd integer is going to be just 1. Now on the other side, I just would like to maybe calculate the n square when n is equal to 1. This is going to be 1, which then it proves that, okay, it works. The sum of the first one positive odd integers is going to be 1. It works in both cases. Okay, let's try another number. If n is equal to 2, that means we'd like to have the sum of the first two positive odd numbers. It's going to be 1 plus 3. And this is going to be, well, this is equal to 4. And if I'd like to have this n square, that means it's going to be 2 square, which is going to be 4, which shows that actually, again, this is equal. So it shows that for p of 1 is going to be, where is it? So p of 1 is true. So the basis case is that p of 1 has shown that it is true. Now, I'm going to assume p of k. If p of k is true, then p of k plus 1 is also going to be true. So what I'm trying to show is that if p of k is true, that means this is the inductive hypothesis. That means for any k that you have, the k, it's 1 plus 3 plus some number. I don't know what to. It's not going to be k though. That's why I don't want to put the k here. So some kind of number x. But here I have k odd positive numbers. So if I have this, that means this is going to be actually equal to this k square, whatever that number is going to be. This is what we're trying to prove, is that for every k positive odd numbers is going to be this k square. Okay, so what I need to show that this k square, which is the sum of the first k numbers, plus this next number, okay, what is going to be that next number? So this x plus 2, this is going to be equal to k plus 1 square. If you'd like to excuse me a minute. Okay, sorry, I had my kid that needed some attention. All right, so what I wanted to say is that if we have this, if we assume that P of k is going to be true, that means if P of k is true, that means it's going to give me, okay, hold on. P of k is going to be true, that means this P of k is going to be equal to k squared. Now, I said that I want to have the sum of the first k numbers. Now, P of k plus 1, what I want to prove is that it's going to be actually this k plus 1 square. But I want to start from here and try to reach that. Oh, if this one, if I add the next one after that, okay, what is going to be the next one? Well, I need to know where am I going to stop. So what is the last number that I'm stopping at? So to be able to go to the next one, right? And okay, let me just try to, okay, so this is the, yeah, so anyways, I think they're trying to do the same thing, except that they use the k instead of me using the x. So because here, yeah, this plus this 2k, okay, so maybe I should use the same, but I'm just going to do something, whatever it is. Okay. So my point here is that my assumption is that I'm trying to solve it, and then if I fail, I will try to see what they have done. But for now, I'm just trying to come up from. So my point here is to have this k plus k square, and I would like to add the next number to it. So what is going to be the next number to it? K square is going to be the sum of the first k numbers that are odd, the k odd numbers. Now, what would be the next number that I need to add? And it should be odd. Of course, if it should be odd, this should be some kind of number that is going to be of this form, 2a plus 1, something like that, where a is some kind of integer. So this is going to be, I would like to prove that if you have this and you add the next one, but here actually, I would like to represent it to be this one is the next one. So how can I do that? Maybe let me just try to represent it this way. Okay, let me represent it maybe this way. If I have 1 plus 3 plus etc. plus a minus 1, 2 times this whole thing plus 1. Why am I doing this? Because the next one is going to be 2a. Oh. This is the next number. This is the number before the next, because the next one is going to be 2a plus 1. So this is a minus 1, and you add another number to it, so it becomes 2a plus 1. So this is the number. So my point here is that this is, you have k odd integers here. Now if that k odd integers are there, now I need to go down. Okay, that's why I don't have a lot of space left. Okay, so basically what I need to do is, now this here, I'd like now to show that if I have these k odd numbers and I add the k plus 1, that this thing is going to be equal to k plus 1 square. So, okay, how can I relate to that? Well, I need to find the relationship between this a and k if I can. Let's try to find, is there some sort of relationship that I can find between the k, which is the number of elements that I have, and that a? Now, for example, okay, let me just go back here. We said for n is 2, we had this. That means or about n is equal to 3. What I'm going to have is 1 plus 3 plus 5, right? And this is going to be this 3 square. Okay, what about n is equal to 4? This is going to be 1 plus 3 plus 5. This is a plus 5 plus 7. And this is going to be equal to this square. Now maybe I can see something. I can see some kind of this k, the number that I have here, this last number. It's okay. I think I can see some result. I mean, let's try it with 5. This is 1 plus 3 plus 5 plus 7 plus 9. This is going to be equal to 5 square. I think I see something. Now if you give me a k, this is going to be 1 plus 3 plus k, right? That k is going to be, now what is that k? Can I find it? This is going to be to this k square, right? But I can find what the k is in terms of maybe that whatever the I said k, that's mistake. Okay, I said some a that makes it k numbers. That said k square. I can find some relationship between this a and k. Can you? I think I just can see it from here. If you can just see it, look, just focus on this last number here, and it has some relationship between the k and the square. Some, like, I mean, not the square, but the number 2 actually. So there's some kind of relationship between the last number and that k. Or in our case, actually, this is the n, right? This 3 here is the n. So this last number, there's a relationship with the n. Look at the last number again. There's another relationship with the n. Can you see it? This number and the relationship with the n. And then I can just find a way to represent this. If n is equal to k, that means I have this 1 plus 3 plus a is going to be k squared, knowing that k a is going to be equal to what? Okay, to make it easy for you, there's some k here. Okay, I can see you're rushing all to answer. Okay, look at this. I think a is going to be 2k minus 1. Okay, let's have a look. When n is equal to 5, what are the last element here? 1, 2, 3, 4, 5. The last element here, a, is going to be 5 times 2, that's 10, minus 1, that gives me 9. Okay, what about 4, when n was 4? When n was 4, the last odd number was 7, which is 4 times 2, that's 8, minus 1, that is 7. When it was 3, that's 3 times 2, that's 6, minus 1, that gives me 5. So that's basically like the idea of this k. What am I doing this? Because I would like to represent this a with some relationship with the k, so I can just later on find out that this is actually equal to that. Is that okay? Can you all see this? Any questions about that? Okay, great. Well, I hope everybody is having the same thing. Yeah. Okay, good. So, all right. So since we all agree on this, let me rewrite this here. This is going to be 1 plus 3 plus etc. And now this is going to be 2. Hold on. 2k minus 1. This is the a. Minus 1. Also, this is a. This is 2k minus 1. This is another minus 1. Oh, I need to. No, that's not. I just messed up. You know why? Because now here I was following a different pattern, where my a here is not the same as this a. This is a different a, because see, this whole thing is normally my a. So okay, so let me just correct myself, just to be on the same, to use the same pattern. Let me just. Okay, let me. So what I'm trying to say is, where is the selection? All right, this whole thing. Oh, that's not what I want. Okay, let me just remove this. You know what? Let me remove it completely, so I can just express it now with my new way, so it can be much easier and less complicated. So now I know that my a here is going to be this 2k minus 1. So if I have for p of k to be true, this means that 1 plus 3 plus, this means plus etc. plus a, that means 2k plus 1. This is going to be equal to this k square. So now if I add the next number after this one, that means this is p of k. What is p of k plus 1? This is going to be this 1 plus 3, too many pluses, 1 plus 3 plus etc. plus this 2k plus 1 plus the next one that comes after this one is going to be 2k plus 3. Right? Because I just need to add two numbers after this one to keep it odd. If this was 3, I add 2, it make it 5. If it was 9 plus 2, make it 11. So it's to keep it odd. And I'm going to say that this is going to be equal to k plus 1 square. This is what I need to show. I need to show that this is equal to this. No, okay, that's... so I need to show that. So to show this, all I have to do now is to try to... Actually, you know what? I know that this is this thing here. It's equal to this. Maybe let me just use a different color. It might make it. So this k square is equal to this thing over here, which is actually this whole thing here. That I just added the next odd number to it to make it this k plus 1. Now all I have to do is to replace these with that. And it becomes actually much easier this way. K square plus 2k plus 3. Keep pressing some button. Okay. So this here, all I need to do is to prove that this is that. And actually, it's not that complicated, because this is, if I just expand this k square, k plus 1 square, this is going to be k square plus, so let me just maybe make it more easy to avoid any confusion. This is equal to this, which is equal to k square plus k multiplied by 1 plus k plus k. This is this one. This is the k square. This is plus k. Now I'm just going to have 1 times k, which gives me another k, and then 1 times 1, which gives me this 1, which is not what I was. This is not exactly the same though. Yeah, that's not the same. Anyways, let's did I do something? Of course I did something wrong. Yeah. Okay, can you show? I've seen my mistake. Can you show me my mistake? Okay, I found my mistake, and my mistake is. So, anyways, let me just continue this while you try to find my mistake. It's not here, so this is going to be equal. Let me move these. While no one yet has to had written something on chat, that means you do not know what my mistake was. So I'm just going to put this aside to give me more space. Nobody found it? Oh. So anyways, let me just write this, simplify. This is k squared plus 2k plus 1. Now my problem is I have 3 here. I should have only 1. And actually, my mistake made me add these 2. So since you did not spot my mistake, let me show it to you. Remember I said the last element should be k plus 2k plus 1. Was it plus 1? No. This is what I did my mistake. I just added 1 here. I shouldn't have added 1 because my a is going to be 2k minus 1, not plus 1. So that was the mistake. So the mistake was that I added plus 1. And then control and plus to make it bigger. Yes. So my mistake is this. This should have been plus 1, not minus. Sorry, minus 1. This is a 1, huh? Because I said that a is going to be the sum of k integers is going to be from 1 plus 3 plus etc. until 2k minus 1. So I have to put 2k minus 1. This is the one that gives me the 2k, the k square, sorry. Now this here, that means here this is going to be a minus, not a plus. And now if I make it minus, add 2 to this minus, this is going to be give me plus, but not plus 3, just plus 1. And this way is my mistake. Now that I have this plus 1, because minus 1 plus 2, this is going to give me plus 1. Then here, this is going to be k square, we said, this part over here. This is going to hold be this thing. And then all I need to do is to have this 2k plus 1, not plus 3. Oh, this is so annoying. I keep doing something wrong. So plus 1. And once I do this, you can see, actually this is equivalent to this k plus 1 square. So I just showed that if p of k is true, then p of k plus 1 is also true. Okay, let's have a look at what they did. Okay, so p of 1 states that, okay, the sum positive number is 1 square, which is true. So for the number is 1, the basis step is complete, all right. The inductive step, to complete the inductive step, we must show that the proposition p of k, if p of k, then p of k plus 1 is true for every positive integer k. So to do this, we first assume the inductive hypothesis, which is p of k is true for some k, and that is, see, it is represented like this. The last, for positive k, so is that the 2k minus 1. Okay, so this is my a, what I presented. So this is going to be this k. I mean, I proved, I showed it to you that way. So, okay, so what I showed here is that this a that I said is actually, this is how I can find that this actually, this is its value, 2k minus 1. So this is how I found it. And then what I like to do is to add the next integer for pk plus 1. For pk plus 1 is going to be this whole thing plus this 2k plus 1 minus 1, which is going to be equal to this 2k plus 2 minus 1, which is 2k plus 1. This is going to give me this 2k plus 1. This 2k plus 2, this is going to be 2 minus 1. So this gives me this one over here. Okay, so this is k square. This red thing is k square plus this is 2k plus 1. And actually they're different, differently, but it's the same logic. So this is going to be equal to that. So if they do the factorization, and that's it. So this shows that p of k plus flows from p of k, that for any k, if p of k is true, then p of k plus 1 is going to be true. So this is how we can prove that by induction. This works for all integers. We just started from the first one and we show it works. Now from any other one, it also works. And that's the mathematical induction, which is approved for all numbers without me checking all numbers one by one. So that's the idea. All right. Okay, what about this one? I'm just looking at the time. We still have some time, inshallah. Okay, so use mathematical induction to show that 1 plus 0 plus 2 to the power of 1. I mean, basically this is actually most likely the 2, 0. I think this should be 2 to the power of 0, which gives me 1, plus 2 to the power of 1, plus 2 to the power of 2, is going to be equal to this thing for all non-negative integers n. So the sum of the n powers of 2. Okay, so whatever the n is, it's going to be like 2 to the power of whatever it is. So let's p of n be the proposition that, I mean, this should be 2. So that's why I say 2 to the power 0 is going to be 1. So this is a mistake. Okay, for every n, so this is the p of n, is that the sum of the 2 power of 0 plus 2 power of 1 plus until 2 power of n is going to be 2 to the power of n plus 1 minus 1 for the for any integers n that is positive, and that is, I mean, non-negative. I mean, positive was greater than 0, it looks like. Can we use it for the negative? I'm not sure. Okay. So let's start with this. P of 0 is true because 2 power 0 is going to be equal to 1. And this is going to be, if we replace this with 0, that means 2 to the power of 1 minus 1, which is going to be correct. And also P of 2, so P of, this is what they're trying to do, P of 2, this is going to be equal to 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2, and this is going to be this 1 plus 2 plus 4, which is going to be 7, which is the same as 2 to the power of 2 plus 1, that means 3, and the whole thing minus 1. This is 8 minus 1, that's 7. So it just shows that the basis step is checked. Now, for the inductive hypothesis, we assume that P of k is true. That means for any non-negative integer k. So again, this is 2 power of 0, and up to k is going to be equal to k plus 1 minus 1. So we assume that this is true. This is what we know is true. We assume, actually, this is the inductive hypothesis. That's what actually they refer to, that IH with inductive hypothesis. Now, based on this, what we need to do is to prove that k plus 1 is going to be actually also true. So what we do is basically we add to this here, again, to 0. This is the P of k. We add to it this one, P of k plus 1, and then we check that at the end it's going to give us the same number. So to do this, I mean, this here, this whole thing is going to give us this over there. Why? Because we said that this 2k is going to give us 2k plus 1, 2 to the power of k plus 1 minus 1. So this is 2 to the power of k plus 1 minus 1. So this whole thing is going to be that plus 2 to the power of k plus 1. Now this leaves us with this here. We just move things around like this here, 2k plus 1 minus 1, let's put it on the side just to put this not next to k plus 1 next to it. So we can see now 2k plus 1 plus 2k plus 1 minus 1. That means this is 2 times 2k plus 1. Because they're twice. I'm having this to be twice. And basically, actually, this is how it works. If you have like 2 to the power of 3 plus 2 to the power of 3, so how many do we have now? It's basically 2 to the power of, you have 2 to the power of 2, 3, and what you do is that you add these things up. So this is going to be 2, 3 plus 1. So this is going to be 2 to the power of 4. Which if you look at it, 2 to the power of 3, this is what? This is 8. And this is 8. 8 plus 8 gives you 16, which is 2 to the power of 4. So that's the idea. So the idea is that when you have these two together, it's the same number repeated twice. I'm just going to make it 2 times 2 this k power of 1. And when you have this thing, this is 2 to the power of 1 multiplied by 2 to the power of k plus 1. So what we do is to sum these powers together, k plus 1 plus 1, and that gives you that. If you just get messed up with this, just try to do some kind of example. 2 to the power of 2. So this is 2 times 2 to the power of 2. Basically what you have to do is this is going to be 2 to the power of 3. Now if it's actually more than, but it has to be the same number though. So I'm not doing something like this and then you can say, oh, this is going to be 3 to the power of 5. No, that's not. They have to be the same numbers. Now this does not work like this. So if you give me 2 to the power of 2 times 2 to the power of 3, that's going to be 2 to the power of 5. You just add these two things together. So which means now, if from this here, this is going to give you 2 to the power of 1 times 2 power of k plus 1. You add this 1 to the k plus 1. This gives you this k plus 1 plus 1, which gives you this k plus 2, which is what we would like to prove. This is what we wanted to show. We wanted to show that if you add this, again, 2 power of 0, I don't know why for some reason I have to correct this. Inshallah, I didn't pay attention to that. And then this is going to be equal to that, and this is what I'm proving. And this is a proof by induction. And yeah, so I'll make the change later, inshallah. Is that okay? I don't know if you're still following. Everything's okay. So it's mainly that thing. All you have to do is to just go for the basis step and then come up with the inductive step, like with the hypothesis, and then from that hypothesis just keep going. There's this one more thing. I mean, there's other examples also with the divisibility, for example, that we're not going to be including, but this inequality, for example, this is also something interesting because actually the inequality is give us more flexibility than when it's an equality. Equality means I have to make sure that they're actually equal, but here I just need to make sure that they're smaller than some number. So if I find a bigger number than the one I'm looking for, it's fine. So for example, if I'm saying that 2 is smaller than 2 to the power of n, obviously to me, I can also show that 2 is going to be smaller than 2 to the power of n times 500, or plus 2, plus 1. So anything that is going to be also bigger is also going to be doing that. So that's the idea behind this. Smaller than gives me some flexibility that I can actually not put only this number. I can put some bigger number. For example, I can just put some 5 to the power of n. If it's smaller than 2 to the power of n, it's going to be smaller than 5 to the power of n, for sure. So that's the flexibility I was talking about. So let's try to see now. Let's have this p of n to be this proposition that n is going to be smaller than 2 to the power of n. So let's try with n is equal to 1. That means do we have 1 smaller than 2 to the power of 1? Well, yes, because 2 to the power of 1 is going to be 2. So 1 is smaller than 2. That's great. Let's try another number just to be sure. That means 2. Is it smaller than the 2 to the power of 2? Which is 4? Well, yes. So now, assuming that we have p of 1, that means it's true. That's fine. Now let's have the hypothesis that p, it's true for p of k. So whatever p of k we have, that means it's going to have that k is going to be smaller than 2 to the k plus 1. So what I need to prove is that now for k plus 1, what I need to prove is k plus 1 is going to be actually giving me that k plus 1 is going to be smaller than 2k plus 1. Oh, sorry. The 2 is not that high. Okay, so 2k plus 1 plus 2, because plus 1 plus 1. Oh, what am I doing? I'm doing something wrong. Hold on. Let's erase everything. I was saying that if p of k is true, that means k is smaller than 2k, not k plus 1. That's what I'm trying to prove. So now if p of k is true, I'm going to prove that p of k plus 1 is also true. So that's my proof that I'm trying to prove later on. But now p of k, that means this. What is p of k plus 1? That's what I'm trying to prove, that k plus 1 is going to be smaller than 2 to the k plus 1. That's what I'm trying to prove. So that's the whole idea behind that. Okay, so now if I'm trying to prove that, now p of k is my statement that is going to be k less than 2. So to complete the inductive step, we need to assume that this is true, and then p of k plus 1, this is what I try to show. I need to show this. This is what I need to prove. Now I need to prove this starting from this, which basically this is what it says, that we need to show that if k is less than 2k, then yes, that's what I need to prove. Now we're going to start from this here, k less than 2k. Now if I multiply this by 2 and this one by 2, what is going to happen? Just remember, we just talked about this, 2 times something, and we're just going to the same, this is like 2 to the power of 1 times 2 to the power of k. This is going to be equal to 2k less than 2 to the power of k plus 1. Okay, so I'm getting closer, because this is actually k plus 1 is what I'm looking for here. Now all I have to do is now try to show up that you know what, I'm having that this here, I need to have something like k plus 1. So but I have 2 k's, so what I can play with it is that basically this thing, I'm going to say 2k means it's k plus k. This is what it says here. So I have this here, and then I can just split the 2k into k plus k, and then these ones I group them together, then that's going to be this 2k plus 1. So we know that this for this is going to be greater than k plus 1. Now it looks like I'm just playing around, but yeah, we said that we're trying to find the k that is going to be positive, right? So as long as k is positive, that's what we're trying to for a positive k, as the smallest k that it can be is 1, which in this case k plus k is actually, if I take this one and replace it with 1, this is going to be much smaller than, because 1 is going to be smaller than my k. Because we said it's going to be now positive integer. So some might say, well, what if it's going to be 1? What if k is equal to 1? Well, then k plus 1 is going to be k plus 1. So it's also true. So basically, if this was 1, I'm just 1 plus 1, and this is 1 plus 1. That's the same thing. Now, if the k is not 1, and then this is going to be 2 plus 1, and this is going to be 2 plus 2. So obviously, it's going to be smaller. So that's the basic idea, is that if I have this, I'll just split this into 2 parts. And because we have that this is going to be smaller than or equal, so I can just replace this, because I have this k plus 1 is smaller than k plus k, which is smaller than this 2 to the power of k plus 1. And that's why I said with the inequality, it's much easier. I don't need to find it equal. I just need to find a smaller number or bigger number that's going to show me that. And then If I have this, well, I'm satisfied with only this first part and the last part to prove that this is actually what p of k plus 1 is about. This is what p of k plus 1, that means it's going to give me k plus 1 is less than 2 to the k plus 1. And that's the idea behind this induction using this inequality. So it's kind of much easier actually than the equalities. All right, time is almost up. Just if you don't have any questions, I'm good. So I think this is what I have. The other things are actually some exercises that at the end of the, yeah, this is some other exercises that you can just practice on. But that's pretty much it. Okay, so if you don't have any questions, I'm going to stop the recording right here. Edit. And then we do the mini test today, right? HTML console control and control N. Okay, let me stop this.